Okay, good. So welcome back, everyone. And sorry if there was a bit of a waiting time. Okay, so we will continue from where we left it this afternoon, and so seeing various entries of the holographic dictionary. So let me just briefly recap what we have seen so far. So we have seen, well, first of all, the IR-UV connection, so the relation between the radial bulk coordinates and the energy scale of the dual conformal field theory. We have seen what's the relation between symmetries, and in particular the fact that global symmetries in the conformal field theory correspond to local symmetries in the gravitational theory. And then we have seen what is the relation between bulk fields and boundary theory gauge invariant operators, starting from known examples in N=4 super-Young mills and type 2b supergravity, where we know exactly how to map the spectrum of the two theories. And so from that, we extrapolated this relation. So we have seen that essentially, so given the correspondence between, let's say in this case of a scalar, a local scalar operator O and a bulk field, scalar field phi, a deformation of the boundary theory of this type is can be thought as being sourced by phi naught, which is the boundary value of the bulk field phi. And this we will be making a bit more precise soon. And so that also extends to other local operators and bulk fields. And so now we are starting to indeed try to make this type of connection more precise. So in particular, we are trying to find what is the relation between operators' conformal dimensions and properties of the dual fields, and we see this is related to the mass. And then we would like to see how are the modes of the bulk fields realized in the dual language. And so for that, we keep using a scalar example. So we start from the bulk, from a scalar in the bulk, and we have seen that in the classical gravity limit in which we are working, essentially we can keep the action up to quadratic order. So the other terms are important for other computations, but for the observation that we want to make, the leading order contributions are enough. So essentially we just need to look at a free theory, a free scalar theory in ADS. And so for that, I was just going through solving the equations of motion, and we will solve them exactly later in these 2 hours, because we will need them. But for the moment, I just wanted to point out what happens in the asymptotic expansion, so near the ADS boundary. So near the ADS boundary, we see that the equation of motion is essentially solved by power law. And so, so here, well, maybe this is not so clear. So let's say that this is delta tilde. So these are the 2 powers that solve this equation, and let's call delta the plus solution, d over 2 plus nu, where nu is this square root, and delta minus the other root. And so the behavior of a scalar field in empty ADS near the ADS boundary is the following. So where A and B are 2 arbitrary functions. And okay, so let's continue from here. So first of all, we see that the two exponents in this expansion are real, provided that the square root is non-negative. So provided that m square r square is greater or equal than minus d over 4, d square over 4. And so this type of bound for the mass of fields, here scalar fields in ADS, is known as the Brayton-Lohner-Friedman bound, or in short, BF bound. And so this bound is particularly important, and actually one can show that the theory, a theory in ADS is stable if and only if this bound is satisfied. And so this is slightly different from what we're used to in Minkowski. So in Minkowski, we have the mass cannot be negative. However, in ADS, also negative masses are allowed, provided they are compatible with this bound. And otherwise, when this bound is violated, as it is the case for negative masses in Minkowski, we have solutions that can grow exponentially in time. And so this corresponds to a tachyonic solution that would cause an instability of the system and which thus are excluded from the spectrum of physical solutions. And so as we know, in Minkowski, this would correspond, well, finding this type of solution would correspond to expanding our theory around a maximum of the potential for the relevant field that we are looking at. And in ADS, somehow, because of the space-time curvature of the space, we can still expand, let's say, around a maximum, provided this bound is satisfied, because there is somehow always some kinetic energy that can actually compensate the effect of a negative square mass. However, if this mass is too negative, we will still have an instability. And okay, we will skip this part. And so this is the bound for scalars, and of course there are similar bounds for the other fields. And let me also mention for completeness that if the mass actually saturates the bound, then actually we have degenerate solutions. And so the expansion of the scalar field actually has logarithmic factors. So it takes the following form, and as it depends on some arbitrary scale, here mu, which is needed to define the logarithm, so to have a dimensionless argument. So is everything clear so far? Please ask questions if something is not clear. Okay. So otherwise, let me continue. So as we saw when we started ADS spacetimes, we saw that anti de Sitter has a conformal boundary, and in particular that light rays can reach the boundary in finite time. And so in particular that there can be energy exchange at the boundary. And this was actually one of the questions that you had. And now what we are going to see is a bit better how we want to impose boundary conditions at the conformal boundary as to have a well-defined notion of energy, that is energy conservation in the full system. So you see that, so let's say boundary conditions for energy conservation. So to go there, first of all, we take the usual approach for a canonical quantization of a field, and here a field in a curved space. So what we do is we take phi, and we expand it in a complete set of normalizable modes, for which then we want to impose appropriate boundary conditions. And so here, normalizability is defined in terms of the finiteness of the Klein-Gordon inner product for a scalar in a curved space. So with respect to Klein-Gordon. Which I will write explicitly. So between two fields, phi1 and phi2. So this is defined on a fixed time slice. And well, as it should, the full inner product is time independent. So we are interested in studying the normalizability of the asymptotic modes for the scalar that we have just found. So these two. And so for real nu, meaning for fields that satisfy the stability we have found, we can verify that, well, okay, for real nu, we also have that delta is greater or equal than d/2. And so you can actually check explicitly, just performing this inner product computation, that the mode which multiplies z to the delta is always normalizable. While the other mode, so the mode z to the d minus delta, is normalizable for nu between 0 and 1, and non-normalizable otherwise. So as always, when we want to quantize the theory and build the Hilbert space of physical state, we use normalizable modes. So depending on the value of nu, so of the mass of our scalar, we have different boundary conditions that we can specify for our normalizable modes, or let's say different quantization schemes. So boundary conditions. So when nu is greater or equal than 1, there is a unique choice, which is consistent with energy conservation, which is setting a of x to 0. So remember, a is the coefficient of the mode that multiplies this factor. So the non-normalizable mode in this range of masses. And so that sets the non-normalizable modes to 0. While in the other range, so for nu between 0 and 1, we have in general, well, we have at least two choices because, well, both nodes are normalizable. So we can pick one or the other, or actually even a combination of the two. So the quantization in which we set a to 0 is referred to as the standard quantization in the literature, because it's the unique choice that we have for nu bigger than 1. And so naturally extends to the entire range of masses. And we often refer to the other quantization, so the one in which we set b, that is the coefficient of this factor to 0, as the alternative quantization. And more in general, as I said, we can also have mixed boundary conditions, which are relevant for the study of some physical problems. So this looks more complicated than it actually is, because I mean, often we have to keep track of all these options. And so for simplicity, I will mostly focus on the standard quantization, which sets a equal to 0. So the coefficient of this mode to 0. And I mean, it's very easy once you have understood the basic case to just generalize it to the other options. Okay, so putting this together, so these normalizable modes which in the standard quantization are the coefficients of, which I call the B, of Z to the delta. So these are the modes, as we are saying, that we use to perform the canonical quantization and to build the Hilbert space of the bulk theory. And so since, as we have said, the Hilbert spaces of the two theories are equivalent, we expect them to correspond to states in the boundary theory as well. It's in the CFT. Okay, so this is like one relation. So we were saying we want to see what do the modes of the field correspond to in terms of dual language, and what we are seeing that the normalizable modes that we use to build the Hilbert state, the Hilbert space, sorry, must therefore correspond by the equivalence of Hilbert spaces to states also in the conformal field theory. And then the non-normalizable modes instead are not part of the Hilbert space. And so if they are present, they are interpreted as instead defining the background. Let's see how I wanted to explain it. Well, let's start writing non-normalizable. Okay, so yes, so we can interpret them as defining the background. Maybe let me also write explicitly that these we use them to build with the Hilbert space. So they define the background. And indeed, we have seen that, so the coefficient of the normalizable mode, which is A of X, again, in the standard quantization, we can see it as effectively being, let me go back to the expression, as being the boundary value of the bulk field. So indeed, so this is the leading behavior of the bulk field as we approach the boundary. And so to make more precise what we were saying before about boundary values of bulk fields, essentially this coefficient A is what specifies the boundary asymptotic value of our field. And so this is clearly up to this factor of the radial coordinate, which makes more precise the identification we had before. So to connect with the notation that we were using this morning, essentially A of X is what before we called phi naught of X, the boundary value of the bulk fields, and equivalently the source for the dual operator. So having a non-normalizable mode turned on corresponds from the boundary point of view to adding a source for O, which is the dual scalar operator to the bulk field phi. And so from the boundary point of view, this is a modification of the boundary action by a classical source. So this is a field which is not quantized in the boundary theory. And so this essentially is a specification of the boundary theory itself. So let me write it more explicitly. So non-normalizable modes, which by making precise what we had before, are obtained as the limit for a scalar, are obtained as the limit at z goes to 0 of z to the delta minus d. So to cancel this radial refactor of the bulk fields as a function of z and x. So they determine the boundary theory itself. So they fix the action. And in particular, they fix which deformations of the actions are turned on. Okay, which essentially makes more precise the statement and the identification we had seen before. And okay, and so one important observation, which was essentially our the question we asked at the beginning, is that this relation implies that this power delta that we found in the solution for the asymptotic modes of the field is the conformal dimension of the dual operator. And so let's see why that is the case. So in a conformal field theory, if we make a scaling transformation, so this goes into x prime, which is lambda x. And then we know that our primary field will transform as O prime of x prime, which is lambda to the minus delta of x. So this is something we saw last time. And so we have also seen that in the bulk, this extends to an isometry where, so we both have x going to x prime equal to lambda x mu, and also z going to z prime equal to lambda z. And so these are symmetries of the two theories. So above of the conformal theory, and below these are the diffeomorphism of the bulk theory. So from the point of view of the field operator correspondence, the bulk field phi is related to the dual operator O, and so this will, well, the scalar will transform to phi prime of z prime of x prime, and equivalently the operator under such transformation will go to O prime of x prime. But okay, so the scalar field, it's clearly a scalar and does not transform under this isometry. So this is equal to phi of zx. And let's see if I want to fit it. And the action is also conformal invariant. Sorry, the action is conformal invariant. Let's say also. So if we look at the full action, so well, we know the usual action will be conformal invariance, and now we focus on the additional deformation that we might have turned on. And we impose that is also conformal invariant. So we impose that if we, let's see what I want to see. Yes, so that if we perform a conformal transformation, this doesn't change. And okay, so this is the boundary value of the bulk scalar. So this is the limit at z prime goes to 0 of z prime to the delta minus d phi of z prime x prime, which is equal to, looking at the transformation for z, to lambda delta minus d phi naught of x. And let me stress that even though maybe the notation is confusing, this delta here for the moment is just the power that appears in the solution to the equation of motion. It's not yet the conformal dimension. And so going back here, so this is the x, so the x prime is lambda to the dx, and then we have lambda to the delta minus d from the source, and O prime of x prime. And so we impose that these two have to be the same for the full action to be conformal invariant, and thus we see that O prime of x prime has to transform as lambda to the minus delta O of x, and thus that indeed delta is the conformal dimension of the dual operator O. So the power that appeared as just in the solution for the modes of the field is the conformal dimension of what we identified as the dual operator to the bulk field. And so just writing it explicitly to answer the first question that we had. So we see that the mass conformal dimension relation is the following. So delta is d over 2 plus nu, which was d squared over 4 plus m squared r squared. And that's for scalars and analogous expressions hold for other fields. And okay, we see also by this relation that we have 3 cases for this operator. So we can have mass equal to 0, in which case delta is equal to d. And this corresponds to marginal operators. So meaning that the effect of the deformation by this type of operators that we perform on the Lagrange does not change with the scale of our system. We can have negative mass squared, which means delta less than d, and so these are relevant operators and thus relevant deformations, which become more important in the infrared. And finally, positive mass square, delta bigger than d, irrelevant operators whose deformation becomes more important in the UV. And so in view also of the UV IR correspondence, this also has a natural interpretation and clear interpretation from the bulk point of view. Because remember that so the UV on the boundary, so let me just rewrite it. So UV on the boundary corresponds to Z going to 0 in the bulk. And remind again that as Z goes to 0, at least in the standard quantization, the dominant, well, always, but okay, in the standard quantization, we identify the dominant as the Z to the D minus delta phi out. And so we see that, so the first case, the one of marginal operators, so the power of Z vanishes. And so, so this is consistent, so this is just constant. And so it's consistent with something that doesn't change in the UV. In the other cases, delta less than d, so this goes to 0 as Z goes to 0, and so this is consistent with something which is less important in the UV. And finally, for delta bigger than d, the vice versa. So it grows, and so this is something which is more important in the UV. Okay, so let me just summarize what we have seen in this part. So if we consider a bulk scalar of mass m, so we have seen that as Z goes to 0, this behaves in the following way, and I will rewrite it explicitly. So we have the mode that goes as Z to the D minus delta, and the subleading mode which goes at z to the delta plus all the other terms. And delta is d over 2 plus nu, d over 2 plus the square root of d square over 4 plus m square r square. And so putting everything together between the bulk and the boundary, we have the following correspondence. So the bulk scalar field phi corresponds to a dual scalar local operator O. The normalizable modes corresponds to states in the boundary theory, and the non-normalizable they correspond to actions in the boundary theory. So they label the different theories that we can have. And then if we stick to the standard quantization, in which we set A of x in which we take A of x to be the coefficient of the non-normalizable modes, or the non-normalizable mode. So we have the following relation. So A corresponds to sources for the boundary dual operator. Where we identify A with why not. And the normalizable modes instead, well, as can be seen, well, I guess we will see it soon and not immediately. But okay, so the normalizable modes essentially correspond to the dual operator itself. So the normalizable mode, they label the states. So they correspond to the dual operator, and in particular, as we will see in a moment, they correspond to the expectation value of the dual operator as a label, let's say, of states within a given theory. And okay, so let me just stress that by this notation, since we know well that in a conformal theory, a one-point function would be vanishing in the absence of source. So by this, I mean a one-point function in the presence of source, which is fixed by A. Okay. And the mass of the bulk field, we have seen corresponds to the conformal dimension of the dual local operator. And I don't know, should I write also explicitly how does it work in the alternative quantization, or maybe that just would confuse you? I'm not sure. Would you like to see it? Yes, no, maybe. No, please don't write in the chat because very briefly. Okay, yes, yeah, it is very brief. Okay, so in the alternative quantization, things are essentially, well, they are similar, but are slightly different. So essentially, we exchange the roles plus some minor clarification. So this is only possible for nu between 0 and 1. Oops. And remember that I'm excluding nu equals 0 because then the solution is degenerated, there are logs, and so it's more subtle. So in any case, here we interpret B as the coefficient, well, as the non-normalizable mode. So things are very similar. So let me copy it. And I don't think it will fit. So. Okay, so that's, oops, essentially the same. So in this case, so B is the coefficient of the non-normalizable modes. So that acts as a source for the dual operator. Identifications are the same, and we use A for the normalizable modes, now in presence of a source fixed by B. So that corresponds, sorry, to one-point functions in presence of a source. And let's say the only relevant thing is that now the mass squared is related to D minus delta. So it's not directly the conformal dimension. And yeah, and as I said, I mean, we can have more exotic things. So we can have mixed boundary conditions as well in this mass range, and they can lead to different things. So in particular, they can lead to multi-trace deformations, which are fixed by the particular combination of modes that we pick. But yeah, for simplicity, I won't go into there. Yeah, let's see. Well, I mean, so this was for scalars. So clearly this also extends to other fields. So let me just write briefly what happens so for a Maxwell field. So AM, so this corresponds, as we saw, to a conserved current. So again, we can solve for the equations of motion. There are modes that we can identify as non-normalizable and normalizable in the bulk. And then this corresponds to setting up sources and for the dual, well, the non-normalizable will correspond to setting up sources for the dual conserved currents. So yeah, I don't want to write everything again because it takes a while. So let me just write the source term. So let's say that mu is the transfer components of the gauge field close to the boundary. So let's say the leading non-normalizable mode of the gauge field close to the boundary. And so this acts as a source for the dual current. And if we repeat the same scaling argument that we had before, we find that the conformal dimension of this dual operator is indeed the -1, as it should for a conserved current which has a protected conformal dimension. And similar, the other important case is that of the stress tensor, mu, which corresponds to components of the well, deviations from the background of the boundary matrix. And okay, I'm sorry, I've inverted the order. I was putting bulk on the left. And again, so this means that the boundary, the transverse components of the asymptotic expansion of the bulk metric source the boundary energy momentum tensor. And again, if we repeat the scaling argument, we find that the dimension of this operator is delta equal t, as it should again, because well, this is the dimension of the energy momentum tensor, and it's protected against quantum corrections. Okay, so sorry, so maybe that wasn't too clear, but okay, let's stick with the simplest example, which is just one of bulk scalars and scalar operators, where I think it's, we have seen it explicitly. Okay, so given this identification, we would now like to see how we can compute correlation functions holographically, which, as we said, are the essentially the basic observables in a conformal field theory. Actually, okay, so here we restrict to Euclidean space. And the idea there is, why we do it, is that if we stick to Euclidean, we can actually forget about all the ordering issues that we have in Lorentzian. So in Euclidean, there is only one correlator that we need to compute, and all the Lorentzian correlators can be computed by different continuations of this unique Euclidean. So in Lorentzian, there is a multitude of correlators like Feynman, Weitman, retarded, advanced, and so on. But they cannot be obtained from the unique Euclidean correlator, so we stick to Euclidean. And okay, so these correlation functions are the basic observables, and in a path integral formalism, we know how to compute them in terms of generating function of the CFT. So let me write it. So in Euclidean, and by this writing, I just mean like the usual path integral with the addition of a source, or better, a collection of sources. So let's say that here by phi x of x, I actually mean a collection of all boundary operators and relative sources. And so the simplest instance here that we can look at is the one in which we have no sources. So Then this one is simply the CFT partition function, and the ADS-CFT, since I mean it's an equivalence between the two theories, this should be equivalent to the dual gravity partition function. And essentially, well, these and the related equations are like the basic way in which to we can implement the duality. So this is a fundamental equation which relates the CFT partition function to the bulk partition function, and that has to hold if the two theories have to be equivalent. And so, so more in general, in the presence of sources, since we say that local operators, local gauge invariant operators corresponds to normalizable modes of the dual fields, and sources corresponds to non-normalizable modes of the dual fields, what we expect is the following. So for the full generating functional, ZCFT, in the presence of sources, we expect that this will be equivalent to the bulk partition function with non-normalizable boundary conditions. So in which we set conditions for the fields at the boundary of ADS, in which this is equal to the dual sources. And this equivalence is again up to the radial powers, to the powers of the radial coordinate z that we had seen before, but let me write it schematically. So this is the equivalence now for the full generating functional. And so, well, okay, maybe let me just write explicitly what I mean by this. By this, I mean that phi of z and x goes at z to the d minus delta phi x as z goes to 0. And so this is the most powerful tool that we have and that we can use to compute correlators at the very basic level, which are the main physical observables we are interested in. And okay, not only those, of course, but okay, as the basic starting points, these are the main ones. And however, in this present form, the equation written in this way, it's not so, I mean, it's very powerful, but it's not very useful in a practical form in this full generality, since we do not know how to compute this gravity bulk partition function independently of this definition. So, however, this simplifies enormously in the semi-classical limit. And so, so in general, we can think that this bulk partition function with fixed non-normalizable conditions for the fields is just written in the path integral formalism as an integral over all fields with fixed boundary conditions. Of some Euclidean action. And so, well, okay, the action schematically is the one that we had before. So Einstein-Hilbert negative cosmological constant with some matter action. And so in the semi-classical limit, in which recall kappa goes to 0, we can perform a saddle point approximation of this path integral, and at leading order, this simply reduces to the on-shell Euclidean action. So where phi c now is a classical solution to the equation of motion, which satisfies the prescribed boundary condition. Okay, so what I want to say here is that, I mean, in this full generality, this equivalence is very powerful, and we can even take it as a definition, maybe one of the cleanest definitions of quantum gravity itself, but it's not powerful from the computational point of view unless we take some limits in which we then know how to define this object independently and then use it to perform computation. And so that is the case in the semi-classical limit, in which we can approximate the full partition function by the on-shell gravitational action evaluated on classical solutions to the equations of motion with fixed boundary conditions. And so in the limit of large N and strong Toft coupling, we have that the generating function of connected correlators, so the logarithm of the what we had before, can be approximated by the on-shell Euclidean bulk action. And let me stress that this type of writing is meaningful only within perturbation theory. So when we write this generating functional, we should think that the sources are infinitesimal, and we should understand this all logarithm to be a power series in the amplitude of these sources. And similarly, on the right-hand side, we should think that the boundary value of this classical solution, that is the non-normalizable modes, are also infinitesimal. So let me stress that this is valid in perturbation theory. And so maybe you might be a bit tired. So I propose that it's not ideal, but I think no point here is ideal to stop. So why don't we take a few minutes break, and we start again, let's say at 45, a quarter to. So let me pause the recording. Okay, so this is essentially the main identification of the ADS-CFT correspondence, and the most powerful one of the most powerful ones from the practical point of view. So I want to make an observation. So in this equivalence, actually, both sides are divergent. So on the left-hand side, we have the usual UV divergences of quantum field theory. This quantities will be divergent. And this, by the UV-IR connection, they correspond to infrared divergences on the right-hand side, which are due to the infinite volume of ADS. So we are integrating over an infinite volume, and that has divergence. So UV and IR divergences. And so, as I was mentioning earlier this morning, the first thing that we have to do here is just to regulate the result. And so for that, we introduce a cutoff, which is a UV cutoff from the boundary point of view and IR cutoff from the bulk point of view. And so from the bulk point of view, this just means that we regulate the location of the ADS boundary by a finite, we bring the ADS boundary to finite distance with epsilon going to 0. And so, okay, so that's the regulation of the divergences, and then this is customary in quantum field theory, and here also extends to this bulk theory. We need to renormalize these divergences. And so for that, we well, we in general need to add local counter terms to make these finite terms. So let me write it. So normally what we look at is the renormalized Euclidean on-shell action, which is the limit as epsilon goes to 0 of the difference between the regulated z equal epsilon on-shell action minus an appropriate counter term action. See? Also at z equal epsilon. And so, as usual, for counter term actions, this has to be a local functional of the classical bulk fields. It has to be a covariant expression, and clearly it also has to preserve the symmetries. We do not want to introduce terms that break the original symmetries of the theory. So local plus covariant plus symmetries. And so the action of this counter term terms in general is to renormalize the divergences of the on-shell action, and also generically to add finite contributions. And so now, given the renormalized action, as we were saying during the break, if we want to compute the connected endpoint correlator, we can simply take n functional derivatives of the generating functional of connected correlators. So if we want to compute O1 of x1, 2 of x2, or n of xn connected, we take n functional derivatives of, sorry, the log connected, renormalized So with respect to sources, so with respect to phi1 at x1, phi2 at x2, phi n at n. So the sources for the operators, and then set all sources, let me just write phi to 0. And so by this main identification, this just means taking the same functional derivatives for the bulk on-shell action. So this means, okay, with the minus sign, as renormalized Euclidean, I see, with specified boundary conditions. And so with respect to phi1, which is the boundary value of the field phi1, and phi n. And then setting the sources to 0. So this is extremely powerful, because essentially what we are doing is that we can compute correlators, which are very hard, if not impossible, to compute in a conformal field theory at strong coupling. And we are evaluating them just in terms of variations of on-shell actions for classical solutions to the equations of motion, which is a much easier problem to solve. And okay, so let me give the results of what one obtains by computing these correlators holographically. Then, as I said, I will move on to a few other points, and then depending on time, I will show you more or less details of the actual computation. So by taking functional derivatives, so if we take one functional derivative and we do not set the source to 0, then we are computing a one-point function in the presence of a source. So that just means holographically to compute the one variation of the renormalized action. And explicitly by pulling out the radial coordinate factors, this means taking the limit as z goes to 0 of z to the d minus delta. Essentially, these are the main for this step, just pulling out the right factors. Z and X. And then, okay, so, well, as I guess you know, once you're given a one-point function in the presence of the source, you can continue to take derivatives with respect to the source and also compute the higher point functions. And so, in particular, coming back to, what's the question? Coming back to our scalar field, which we have lost somewhere here. Which has the following behavior. At z goes to 0, what one can show is that for the one-point function in the presence of the source, the holographic computation gives 2 nu, I mean fixing even all factors, times b of x. So the one-point function in the presence of the source, as we anticipated before, is given by the normalizable mode b of x. And so really the normalizable modes essentially label the states, well, correspond to states, sorry, as labeled by the expectation values. And then, well, one basic check that one can have why this should be the case is that both quantities, so both this expectation value and the normalizable mode, transform in the same way under dilatations. So let me just show it quickly. So for the expectation value, so under a dilatation, we know that this goes as lambda to the minus delta O of x phi, where, okay, x prime is lambda x. And the scalar instead does not transform. And so for z going to 0, this contains the mode z to the delta b of x. And so this invariance means that lambda to the delta z to the delta b prime of x prime has to be equal to z to the delta b of x, and thus indeed that b prime x prime is lambda to the minus delta b of x. So okay, this is just a consistency check that what we have written is not crazy. So the two objects transform in the same way under dilatations and by explicit computations that hopefully we will see to some extent in a moment. One can find these explicit relations, including fixing coefficients. And okay, so this is for the one-point function in the presence of the source. If instead one, for instance, the two-point function in absence of sources, and so recall that in a conformal field theory, two-point function vanishes if and only if, sorry, it's non-zero if and only if the conformal dimensions of the two operators are the same, and that we can set an orthonormal basis in which it vanishes unless the two operators are the same. And in any case, so this two-point function, one can compute it holographically following this simple, this in principle simple procedure, and verify to be indeed given by the expression that we expect for a conformal field theory, where we indeed also fix these constants. So that just to say that this holographic computation for correlator reproduces these these known 1 and 2 known results, and of course it gives us access also to more complicated correlators which are not accessible directly by standard field theory techniques. Okay, so let's come back to this computation in a moment, hopefully. And let me first make two other points that are important for the next lectures. So the first one is the relation between the eternal black hole. So it's a particular entry of the dictionary for two particular states. And so the relation between the eternal black hole and the so-called thermophile double state. Sorry, maybe before I continue, are there more questions about the correlators? And as I said, hopefully we will be able to go back to them in a moment. Otherwise, for skills, I can send you some notes about the computation itself.
Can I ask a question?
Sure.
Well, it's clear to me how to go from the ADS correlator to the CFT correlator because it is sufficient to take the limit of Z to 0. But I don't understand if it is possible to do the opposite, to do a computation in the CFT and then obtain some information about the gravity theory in the bulk.
Right, so to the extent by which you can exploit this equivalence, yes, I mean, so the easiest directions in which we know, I mean, in which this equivalence gives us access to something that we do not have access otherwise is the one in which we are using it now, right? So to have access to correlators at strong coupling using classical gravity. Of course, it's an equivalence, so it holds in both directions, but in general, it doesn't give us access to non-trivial information in the or not otherwise known information in the other direction.
Okay.
No, maybe you had something else to add. I don't know if you have something specific in mind. I mean, if you know, yeah, like this partition function to or generating functional sources to any extent, of course, yeah, it gives access to a full quantum gravity partition function that is something we do not know how to define independently. So
yeah, no, maybe I have to think more about this, but yeah, my mind was a loss of information by taking the limit of Z to 0, but maybe I just have to think more about this.
what do you mean by the Z to 0 limit? Sorry.
Well, when we have to project the operators on the boundary, we have to take the limit of Z to 0.
Well, I'm not sure I'm following at which step. I mean, at which step did I take at Z to 0 limit here? I mean, I'm looking at the asymptotic behavior of the boundary, and that fixes the boundary conditions.
Yeah, in the next page, in the next slide, when you computed yes, in the first line. The first line you take.
But this is just to pull out. So sorry. So maybe here I wasn't clear. But so phi is the source, and it's the boundary value of the field, but up to some radial powers of the radial coordinate. Here I was just pulling out these factors, which appear in the relative definition between this phi and this capital phi, as to take functional derivatives with respect to the field itself.
Oh, okay.
Yeah. So it's not like a projection. I mean, here I'm just pulling out the relative factors which exist in the definition of these two quantities.
Okay. No. Okay.
Yeah.
Okay, now it's clear. Thank you.
Okay.
Sorry, I have another question about the 1-point function. So if we have non-trivial boundary condition for the sources, then the 1-point function will not be 0. I mean,
yeah, exactly.
So can you give us more insight on
this? So if you take vacuum expectation values in a conformal field theories, they will vanish because otherwise they will break conformal invariance. But if you are in the presence of a source, so you can think that essentially the source fixes the background state. So effectively, you're not anymore actually computing a 1-point function. It's more like a 3-point function. You are in some state which is set by the sources. Yeah, and so that's why it doesn't vanish.
Okay, thank you.
Okay. So as I said, I mean, also depending on your interest, we might or might not see this computation because, yeah, I think I'm not too optimistic with the time that we have left. But I will need to move also to two other important observations that you will need. And then if you're interested, we can go back more to the correlator. And I'm happy with the question time to address questions if you have them. Do you have another question? I was hearing something, but maybe it was just some background. Okay. So the other one other ingredient that I want to introduce is the relation between two very special states. So on the one hand, the eternal ADS black hole, which we had seen by looking at studying ADS, and the so-called thermophile double state. So let me make a drawing. Okay, I draw it flat as it is in 3 dimensions. Okay. In any case, so let's say that this is the Penrose diagram of the eternal ADS black hole, which we have seen. It has 2 asymptotic boundaries. Let's call them right and left. And we had seen that in the static geometry, we have time flowing upward on one boundary and downward on the other boundary. So let's call it T right and T left. So this geometry has 2 asymptotic regions and 2 boundaries, and so this naturally suggests that the dual to this bulk solution might be given by 2 copies of a conformal field theory, each living on one of the 2 boundaries. And the question is, though, in which state? And so the very famous proposal of Maldacena in 2001 is that this eternal black hole corresponds to a tensor product of the 2 conformal field theories, left and right. Oops, conformal field theory, left and right, in a particular state, which is known as the thermophile double state. And I will explain in a moment what that is, but let me just write explicitly the state first. E and left, so in the energy basis of the 2 theories. And so beta here is the inverse temperature, which corresponds to the Hawking temperature of the black hole. And so let me explain a bit better what this thermophile double state is, since you might not be familiar with it. So this is essentially what it's called a purification of the thermal state of a single copy of the CFT. So purification. Let's say of I don't know, CFT right, but okay, because it works. Doesn't matter if left or right. And by purification, what we mean is an entangled Blur state, which is obtained by starting from the thermal state in the canonical ensemble. So let me write it. So we start from a thermal density matrix for one copy of the CFT, where H right is the right Hamiltonian. And so in terms In terms of energy eigenstate, we write it as e to the minus b e n, right? And so we start from this Gibbs state for one copy. Then we take a copy of the system. So we take a copy CFT left with identical Hamiltonian. And we set the full system in this entangled state. And so this is what is known as a way, as I said, to purify a thermal state, that is to enlarge it to a entangled pure state of a larger system. And so, so then the idea is that if we then restrict to any of the two copies, that is to subsystem left or to subsystem right, the reduced density matrix, so rho right or rho left, which we obtain by taking the trace over the left or the right component, sorry, trace over the left or right part of the full density matrix, we have a Gibbs state. Okay, so I'm not sure how many of you are familiar with this, but okay. So essentially the idea is that if we look only at one boundary, so at one copy of the CFT, which will be the case in the usual way in which we think about black holes, what we see is a thermal state. And that's manifest in the fact that once we take the trace of the full density matrix and we reduce to one or the other boundary, we do see a thermal density matrix. However, once we consider the full extension of the spacetime, which is the eternal black hole, which has two boundaries, and then we ask about the state corresponding to the full geometric system, then this is naturally corresponds to this thermophile double state, which is an entangled state of the two boundary tiers. Let me see what else I want to say. And okay, and as we said, in this eternal black hole, once we extend the symmetry under time translation that we have in one asymptotic region, and we extend it to a global isometry of the full space. So the way to do it is for the other asymptotic regions is to take time running in the opposite direction. Then, okay, from the bulk point of view, we have a global isometry, and correspondingly for the that's right, global dt, so a globally defined time-like Killing vector. From the boundary point of view, this corresponds to the fact that this dual state, thermophile double, is invariant under the time evolution with h given by the difference. So the fact that time is running upwards means taking the full Hamiltonian to be h right. Sorry, the time is running in opposite directions means taking the full Hamiltonian to be h right minus h left. So once we take the time-dependent thermophile double state, which is just the evolution of the t equals 0 thermophile double, And so you can check it immediately that, so the two Hamiltonians are the same, and so they will have equal and opposite eigenvalues, and so this is indeed time independent. And one precision also here, it's in order that, okay, given the time invariance, so the existence of a globally defined time-like Killing vector, we could think of any time slice, which we call are of this form here, to be equivalent, and so the dual state to be defined, the dual state corresponds to any such time slice, but the way in which we normally think about it is as the dual to the t equals 0 time slice. And then when we talk about this type of evolutions, this maps into the other time slice in the bulk. And so the main observation about, well, one of the main, there are many, but one important observation is that indeed, if we restrict to one asymptotic region or to one of the two subsystems, left or right, we see a thermal density matrix or a asymptotic region of a black hole. However, the full system is comprised of two entangled copies. So the left and right system are not interacting or coupled by some, not interacting through some coupling or Hamiltonian. They are really only entangled, one with the other. And geometrically, in the duality, the interpretation of this entanglement between the two theories is the fact that the bulk in the eternal, well, the two asymptotic boundaries in the eternal black hole are connected in the bulk through the geometry, and in particular through the Einstein-Rosen bridge of this black hole. And so to summarize this observation in a very famous slogan, this type of geometry really realizes the fact that the connectedness of space-time corresponds to the entanglement in the dual conformal theory description. And this is also known, let's say, this realization of this very profound relation that we are only starting to understand also goes under the name of ER equal EPR. So the fact that the Einstein-Rosen bridge in the bulk is the equivalent of the EPR correlations of the boundary state. And that's a name that was given by Maldacena and Susskind in 2013, let's say, as a label or a motivation for this entire program, which then tries to understand spacetime itself in terms of the entanglement structure of the dual theory. And so let me make a drawing to show a bit better what do I mean. So let's stick to the three-dimensional case. So let's say the eternal, for simplicity, so the eternal BTZ at t equals 0. And so the spatial boundary coordinate is a circle. And so we can draw the horizon. Okay, so sorry. So this would be the extension in the radial bulk coordinate. So this is CFT left, CFT right at a fixed time, which so they live on a circle. And so this is the representation of the bulk, and this will be the horizon, or better at t=0, the bifurcation surface. And so this is just a way in which we can visualize the relation between, indeed, the connectedness through spacetime and the entanglement, which is geometrically between the boundary theories, which has this geometric representation. And this is very inspiring. And as we're saying, I mean, we are, as you will see in the next lectures, this is a relation that we are only starting to understand. And let me make other two observations here. So in particular, once we take correlators in these thermophile double states of insertions which are on the two boundaries. So let's say that we take an operator which is defined on the left and an operator which is defined on the boundary theory. So this type of correlator from the boundary point of view is different from zero because the thermophile double state is an entangled state, and thus there are correlations between the two boundaries. And from the bulk point of view, instead, it's clear why, if we compute holographically this type of correlation, we in general expect a non-zero result. And this is because the two asymptotic boundaries are connected through the bulk. And so we do expect a non-zero overlap geometrically between these two states. So the state that we can obtain by inserting an operator OR and letting act on the thermophile double, and O left doing the same. So this is just another hint of the relation that we have between space and geometry and entanglement. And so the final observation that I want to make is something that you will need, I assume, for Jan's lecture as well, is that, so we have chosen to evolve our system using H total Hamiltonian to be the difference of the two. But we have some freedom here, and actually we could have chosen to evolve our state also with the sum. And so if we do this choice for the total Hamiltonian of the system, the thermophile double state then is time dependent. So then if we act with this Hamiltonian and we compute the time evolution of this state, we will find a non-trivial time dependence. So I'll just check it. Minus t and left, and right. Even though if we if we do a partial trace, so if we let's say reduce to the density matrix of one of the two copies by tracing over the other copy of the system, you can check very easily, explicitly, that this will be time independent. So the full system evolves, but once you specify, you just have access to one asymptotic regions, then you don't see any time evolution. And so geometrically, indeed, this corresponds to not having anymore a globally defined time-like Kinlin vector, but instead to continuing the single-sided Schwarzschild ADS geometry to a solution in which time runs, let's say, upward in both asymptotic boundaries. And so time translations remains an isometry for the two regions as taken alone, as reflected to the fact that once we trace out the left or right part of the thermophile double state, the density matrix is independent, but there is not anymore a global isometry of this entire eternal black hole. And so now, if we look at constant T slices, so the T equals 0 slice is the same, but now as we evolve it, so the full geometry has some non-trivial time dependence. And in particular, this time-dependent version, let's say, of the eternal black hole and of the dual thermophile double state is particularly interesting for entanglement considerations and for a very large variety of applications of these ideas. And you will see selections of those in the next lectures. And okay, I'm sorry, it looks like I won't have time for the holographic two-point function. Let me just say the last thing of today that I wanted to say, which is a comment about the spectrum or the class of holographic conformal field theory. And sorry, before I move, please ask me questions about the eternal black hole and the thermophile double states if you have them, because maybe that was a bit different from maybe what most of you are used to. If you have any. Okay, so if not, let me make the last comment for today. So as I said, we think that in general, holographic conformal field theories is a broader class of the specific string theory realizations that we know of. And so in what is known as the bottom-up approach, which essentially is in the spirit of effective quantum field theory, what we do is to think as of the ADS-CFT correspondence as a duality between a class of conformal field theories, which we call holographic, and which satisfy some constraints on their CFT data, that is on their spectrum and OP coefficients. And that essentially these constraints allow for a dual geometry, well, not necessarily geometry, but for a dual quantum gravity description in asymptotically ADS spacetime. And so if we, I don't want to, I mean, so let's say that what exactly are these constraints and how to make them very precise is still debated. I mean, there is a lot of ongoing research also within the conformal bootstrap program, to try to identify what are the constraints on CFD data for our theory to be holographic. So there has been a lot of progress. I just want to comment here on the basic requirements that we know that a conformal field theory has to satisfy in order to have a well-behaved semi-classical gravity dual. And so there are at least two constraints that we expect. So the first one is that the conformal field theory has to be strongly coupled. And this is because if the field theory was weakly coupled instead, there would be too many operators. And let me specify what I mean by that. So if, for instance, we take a free scalar field, so we know that there are conserved currents for every integer spin. So essentially, if we have a free scalar, that's just one example, to give you an idea, then we can make conserved currents schematically of this form. So just by acting with any number of derivatives. And so this gives conserved currents of arbitrary spin. And so from the bulk point of view, as we have seen, because of the field operator correspondence, this would require the existence in our gravity theory of lots of massless or very light high spin states. And while this is something that we do expect in string theory at high enough energies, it's surely something that we do not expect in a low energy effective field theory. For instance, it's surely not something that we do expect in Einstein gravity, in which we have at most spin 2. And so this translates into the fact or the requirement for our conformal field theory that they need to have what is known as a sparse spectrum of low dimensional operators. And this is also known as a large gap in the spectrum. That's also how it is often referred to. And so the idea is that we do need a gap between the low energy fields and the stringy excitations. And we need only few of these low dimensional operators, and so the spectrum needs to be sparse enough. And there are some attempts at and successors at making this sparseness condition more quantitative. But okay, so the basic requirement in general terms is this one. And this is something, as we just saw, that can only happen at strong coupling, because at free coupling, we end up generating lots of operators. So this is why we do need the theory to be strongly coupled. And the other basic requirement that we need is that our theory needs to have a large number of degrees of freedom. And indeed, we have seen in the super Yang-Mills example that the number of degrees of freedom was counted by n, capital N squared. And that we, in particular, we needed to take n large to be, for gravity to be weakly coupled. And this is true in general as well. And let me just point out one way to see it. So as you've seen, I think in the string theory course, the two-point function of the stress tensor is fixed by conformal invariance up to a single coefficient. C, and then so this multiplies a known, let's say, a known function of the insertion. And so this C, as I hope you've seen, well, I'm sure you've seen, is a measure of the number of degrees of freedom. So again, if we are in a free theory and we have lots of fields, their stress tensor would add up, and so effectively the individual C's would add up, the individual constants would add up, and so this counts the number of degrees of freedom that I have in the theory. And so in holography, we have seen that the stress energy tensor is related to the bulk graviton, and so a two-point function of the energy tensor in the boundary is related to a two-point function or graviton scattering in the bulk. And so the process of graviton scattering is governed by G Newton. And so essentially, schematically, this constant C, or central charge, is related to 1 over G Newton. And so we see immediately that if we want a weakly coupled theory of gravity, that is a theory in which we send G Newton to 0, we need C to be very large and thus a very large number of degrees of freedom in our theory. And so if we put together these two requirements of strong coupling and sparse spectrum of low-dimensional operators and an overall large number of degrees of freedom, we see that essentially we want a lot of states at high energies in our theory and very few states at low energies. And so, roughly speaking, we want our conformal field theory to have a confining behavior. So this is very similar, for instance, what happens with QCD, in which a large number of states are accessible at high energy and very few are accessible at low energies, in which we have confinement of the quarks. And okay, as I said, there are several attempts to make these basic requirements more precise, and partial success so far, but okay. Yeah, this is what I wanted to tell you and what would be enough for the following discussion. So I'm sorry for those of you who, probably most of you, who haven't seen the computation of two-point function. So if people are interested, what I can do is just give you my notes for them if you want to have a look, and then you can ask me questions. And so now I will stop the recording, and I first of all thank you very much for the attention.